Hello, good afternoon, everybody. It's 1 o'clock now. I think we're about to start. This event is brought to you by the IBM MHV TVA, which is an affiliate of the IBM Academy of Technology. The webinar today is going to be on compact qubits in quantum computing by Rashid. Is a developer, a researcher in IBM Q Computing. Before we start, I'm going to ask you in order to receive 1040 credit, make sure you log on when you go back to your office, right? And click on 1040 credit so that you could get your credit after you get back to your office, okay? Without any further ado, I'll pass the mic to Rashid.
Thank you, Mark. So, a slight correction. So, I'm not affiliated with IBM Q, but I've done some work with them. And so, this talk is mainly a tutorial, and at the very end, I'll also present about some of our original work as well. So, I'd like to start by talking about why we need a quantum computer, because we already have access to these wonderful mainframes and GPUs, etc. They can give us lots of floating operatings per second, and these are still going to keep increasing. So why do we need quantum computing? So this kind of flop increase will only provide us with a linear increase in the types of problems that we can solve. However, there are some other problems where such linear increase is not going to be sufficient, and we want something beyond this linear speed up. And so we are trying to basically target that space by introducing what we call these qubits. And so with the promise of solving new problems in polynomial time that we could never achieve with a traditional mainframe. Maybe I'd like to start with some computer science background. So many of you must know Alan Turing. So he invented this Turing machine concept, which is basically a machine with a read-write head, which is shown as the red rectangle. And then you introduce an infinite tape, which is the blue tape. So this tape contains those boxes. Each of them could be either a 0, a 1, or a space. So basically, you would be mapping your problem to that characters and number space. You're allowed to move this infinite tape back and forth one step at a time. And there are a finite number of states that you can do with that head. Basically, a finite state machine controls what you are going to do with the head, but that state machine is not infinite. So it can be a large number, but it's not infinite. So the computation that you can do with this machine depends on only two things. The current state from that state machine, and what you are reading from that infinite tape at that instant. And then, based on the state machine, you are going to do something else next. So what is important to know is this model is not there to model, let's say, a modern computer cycle to cycle, but rather it is there to model how it achieves a computation. For example, you may be able to use some parallel Turing machines, parallel infinite tapes, to model a modern multi-CPU computer, but it's not going to be a cycle-accurate computer. But at the end, the computation you should be able to model with a Turing machine. So the reason I introduced it is that so computer scientists also deal with some complexity classes. So there are a few well-known complexity classes in computer science, the P-space and P-space. So P-space is, for example, the type of problems that you can solve in polynomial time. This is like the ideal types of problems that you would want to target. And for example, our traditional computers are great, so we can keep increasing the problem size, but as long as we throw in more computing power, we can still solve those problems efficiently. For example, many of the sorting type of algorithms can be considered to fall into that space. And then, for those of you who may be dealing with electronic design automation, a lot of those problems fall into the NP complete or NP hard categories. So they are relatively difficult problems. So the interesting thing with the NP complete is that you cannot easily find a solution, but if someone gives you a solution, then you can easily check whether the solution satisfies the given problem. And NP hard is a bit more difficult, so it is at least as difficult as any of the problems in the NP space. But these problems can be reduced to an NP hard problem in polynomial time. So usually the way we go after these NP hard problems is we come up with a heuristic that kind of gives a approximate or efficient enough solution. And then outside this we have the P space. So there are some problems that are in NP, and we don't have quite efficient algorithms for them. For example, factoring prime numbers is thought to be in the NP space, and it is not in P or not in NP complete. So these, although there is sufficient evidence that these categories look like this, actually it is not known whether P is equal to NP or NP is equal to NP complete, and this is actually kind of a conundrum in computer science. But this is the most state-of-the-art knowledge. So let's talk about this factoring. For example, let's take into account this RSA factoring, which is a very stable public key crypto system. And it stands for Rivest, Shamir, and Edelman, the three researchers who came up with this method. So in this method, you have some public keys that you release out there, and everybody can read those. For example, E and N would be those public numbers. These can be quite large numbers. But you have a private key. In this case, it is D. Whenever you want to decrypt a message, you are going to use your private key, and no one else should have access to that key, otherwise they can read your messages. So this, one of the public numbers, N, is actually picked to be a multiple of two prime numbers. And those prime numbers should also be kept private. And if you release one of them, then we know that this D, which is your private key, is given by a formula that depends on the public numbers N and E. And there's a function which we are not covering here called alpha. But if someone knew one of those prime numbers, they could easily compute that alpha, and they could easily have access to your private key D. So the way the encryption works is, let's say you have a message that is encoded and in zeros and ones that is trying to send to you through a public channel. They would take the power to the E of this message. So I'm going through the fourth bullets. And then they will take a modulus with respect to the public number n. And that is that final computed value they will send through the public channel. And the receiver is going to receive that portion, so up to here, is going to take a power of D using his own private key, and then take a modulus with respect to n to get to decrypt the number. So the complexity of this system has to increase because we have access to these powerful machines. For example, there are some challenges out there. There's a RSA 896 challenge. The 896 is the number of binary digits, and it corresponds to a 270 decimal number. And if you're able to find the two prime numbers that make up this number, there's a prize out there right now that you can get yourself a good bonus by solving that. So these kind of things, of course, it's going to be solved in few years, but they're going to try to increase the number of numbers in the RSA to keep the RSA strong enough against attacks. So what the quantum computing is giving us as the premise is that since I mentioned that that factoring is in the MP space, we think that it could be somewhere around here, and we are introducing a new complexity class, which is giving us some new types of problems that can be solved efficiently with a quantum computer. So thus, if we have these powerful quantum computers, then we can easily crack an RSA, so we will need to figure out new encryption and decryption methods. So let's talk about what these qubits are. So when we talk about a qubit, so by itself it stands for a quantum bit. It can be used in the context of either an information carrying indicator, but sometimes instead of calling something a qubit device, we can also call it a qubit. So it can be an indicator or a device depending on the context. And some of you might have heard that with a qubit, you can indicate an infinite number of values. So, but how are you going to define this? Sometimes it is easier to understand something by modeling it. So, are we going to, let's say, call 0 and 1, and then have something linear in between to indicate all those infinite numbers? Are we going to have the angles indicate those, or phases indicate those? Seems that those are more similar to analog systems, but there's a more complete model known as the block sphere, which is going to assume that you have your traditional states, let's say 0 and 1, and at the top you put one of them. It doesn't matter actually which one you assume to be at the top, but let's say 0 is at the top and 1 is at the bottom. Now there's an arrow that can go and point anywhere in that sphere, and so basically you are going to have two angles defining where that arrow can point, and we are going to assume that the arrow has to touch the surface of the sphere as well. And then I can define two parameters, let's say alpha and beta, and I can also write that alpha and beta in terms of those two angles, and then I can uniquely define where this arrow points in the sphere. And when I'm going to measure, I need to, at the end of a computation, map these back to the standard zeros and ones that we know of, because we are going to possibly use standard computers to send in a computation and pull computation out of a quantum computer. At the end, so I need to map this arrow back to either a 0 or a 1. So I need to decide maybe which way it is closer, and then that could be how I'm going to measure the qubits. There are also some mathematical models. So we are not going to discuss too much about this, but whenever you see quantum computing, you will be using these notations called bra and ket. So the A is read as bra A. Actually, what this bra operation does is it indicates a row vector in linear algebra. And the ket, for example, ket B, it indicates a column vector. So we are not going to use them too much in this presentation, but we can also describe the state of a qubit using linear algebra and a vector. For example, that 0 state at the top of the Bloch sphere, I can describe it as a 1, 0 vector. And let me describe the one at the bottom of the Bloch sphere as a 0, 1 vector. And then I can bring my alpha and beta parameters, and then the whole qubit state I can indicate as a alpha and beta vector. So the two of them will be defining the state of one qubit. Well, what if I had two qubits? Then from those 0 and 1 in the Bloch sphere, I will have instead 0, 0, 0, 1, 1, 0, 1, 1 configurations. And each of them can be represented by a vector. So if I had 3 qubits, I would have 8 different vectors that indicate those states. This is kind of like a one-hot coding. And then I can similarly have some alpha and beta introduced, and then using a four-valued column vector, I can uniquely describe the state of 2 qubits. Right. So again, for 3 qubits you would need 8. For 4 qubits you would need 16, etc. Okay. So then maybe I need to introduce some operations on these qubits, and these operations also can be described as linear algebra. And in this case, they will be described as matrices. And at the top, I have listed some common quantum gates. For example, a Hadamard gate, which usually takes a qubit pointing to one of those states and flips it to the circumference of that Bloch sphere. And there are some rotation operations: X rotation, Y rotation, Z rotation. I can change the phase of the qubit by, again, rotating around that circumference. And not all of these gates are actually implemented in our quantum computers, but there's, for example, some of them are extremely critical, like Hadamard and CNAT. But maybe I don't need to have a pi over 8, because there are other ways to kind of describe a similar gate operation by adding multiple more common gate operations. So those ones on the top left, they are all one input, one output in terms of qubit counts. Now the gates on this side, in contrast, now you are inputting 2 qubits. So each of these lines indicate a qubit entry, and then you're getting 2 qubits as your output. So this can be described by a 4x4 matrix. So the first one is a controlled NOT operation. Depending on the state of the top qubit, you decide to flip the bottom qubit or not. So So in this case, the top qubit is the control qubit, but in another implementation, you could have flipped this sign the other way around, which will make the bottom qubit to control the top qubit. So it's also important to initialize the qubit, because all of you know that if we had garbage in, the output would be also garbage. So we need to make sure that the input can be set to the values that we desire. And so we will try to basically initialize the qubit states usually to either that 0 or 1 state in the large sphere. And so this can be done in various ways depending on the architecture, but sometimes it is just possible that you wait long enough that the qubit falls to the ground state from an energized state, which could be, let's say, the 0 state. By just waiting, let's say, a few microseconds, you end up initializing your qubit to that ground state or zero state. Actually, this is how we are initializing our qubits at IBM. But there could be other ways. For example, you could have assumed that you are going to initialize them by sending a laser and then energizing them to the one state. So that could have been an alternative option. So some of you might have heard that there is this concept of entangling qubits. And actually, this can be easily done by just using a controlled NOT gate for your two qubits. So the applications of this is, for example, in cryptography, you entangle two qubits, and if someone tries to interfere with one of them and tries to measure, by just looking at the other qubit, you are able to tell if the other user has interfered with you or not. So let's say we have applied some CNOT gates and entangled our system, and then the two qubits are described using this equation, which means that each of those configurations, so qubit 1 having the value of 0 and qubit 2 having the value of 0, this first one here, that has a chance of the square of that constant, which will be 1/4. So, and similarly, basically from this particular equation, we say that the chances of all of these are 25%. However, if you end up measuring the first qubit, and let's say you found that the first qubit's value is 0, then it's going to change the likelihood of the second qubit being a 0 or 1. And now the second one will have a chances of being a 0 of 1 of 50%. Basically, so this is my definition, but if by measuring one of the qubits, you are able to change the probability of the remaining qubits, then maybe that would indicate that those qubits were entangled with each other. So what can we not do with qubits? We cannot start with one qubit and have two qubits having the exact same value. And there's a theorem, and there are some proofs that support this as well. And also, there's a related variation called the no broadcast theorem. So you can also not take one qubit and try sending it to more than two people or targets either. And also there's another related theorem. Let's assume that you started with two qubits that are somehow showing the same value or same state. Then it is also impossible to delete one of those states and assume that the other one will stay intact. So even though we cannot copy qubits, it is interesting to find out that it is actually possible to move them around. So those two lines are showing two qubits coming into the system, and there's a special sign for this, which is the one in the middle, using just a cross sign. Indicates that we are moving one qubit to the top and moving the other one to the bottom line. And the way to implement this can be basically using 3 CNOT gates. You start with either the bottom one as the control, or other way around. It would give you the same solution. So then, how can we combine all of these and come up with things called quantum circuits? So this is a representation of the quantum circuits. You will have each of these lines indicate qubits. So you start your computation from the left, and at each time scale, you will be applying some gates to these qubits, and some of the qubits will not be worked on in a given time step. So let's say the first time step, qubit 2 gets the Hadamard operation, qubit 3 gets a Pauli X operation. It is possible that the remaining qubits might lose their state, so there may be some way to rectify and maintain their information. And then you come to the second step. Let's say the qubit 3 got a Hadamard, and then here's a controlled NOT operation. So the state of qubit 3 is going to determine whether qubit 4 should be inverted here or not, etc. So this is called how many operations you can apply back to back without introducing significant errors. Is called the depth of this circuit. And at the end, you are going to measure these qubits because we don't have an understanding of that Bloch sphere. But if we map everything back to a 0 and 1, then we'll have a clear understanding of what was achieved. So this step is a destructive step. It is going to assign your qubits in the Bloch sphere to either a 0 or 1, most likely whichever side it is closer to. If it's in the middle, probably you are going to have either a 0 or 1 assigned randomly. If you measure, you can never go back from here. But other than that, if you have not measured your circuits, so these circuits are called reversible. Actually, you can, let's say you are here, you can apply these gates in the reverse order, and you should be able to get back to the original state if you desired. So when these qubits are measured in a lab, there are a number of parameters that are of interest. And the first 4 are usually very important at the qubit by qubit level. And you should be familiar probably with the T1 and T2. So these names are much different than the way the hardware people use them for. T1 corresponds to a relaxation time. Let's say you have excited your qubit to an excited state, let's say from 0 to a 1 state. How long can it stay there and maintain that state? Because it's going to want to drop back to the ground state. And then you would try to measure how long it is taking for you. You would ideally have this number to be very large, but you will find that it is in the tens of or hundreds of microns, depending on the qubit type. The T2 is related to the phase angle around that Bloch sphere. Is it able to maintain its phase long enough? And again, you would want this number to be long. So the Ramsey and Rebai are very similar to the traditional ways the physicists have used them over so many years for various applications. And at this circuit level, then you care about these gate error and readout errors, whether when you start adding these gates, you are able to have an error-free computation or not, and you quantify with them. So there are a number of different qubit types, and then this table is kind of my interpretation of their being good or bad for various aspects. So, for example, the T1 and T2, are they long enough? Are the qubits scalable? So can I build a quantum computer with 100 qubits, 1,000 qubits? And who is the main supporter in the industry? So IBM is mainly focusing on circuit-based qubits, and it is giving us good T1 and T2 values. So it is not as great as maybe a trapped ion or vacancy-based qubit type, but it shows much better scalability with respect to those. And if you only have access to few qubits, you can never solve interesting enough applications. So you need to get to at least 200 or above. And I'm not claiming these methods are not conducive to those numbers, but so far, since we are trying to leverage our knowledge of silicon for scalability, the silicon-based ones are looking pretty well. And there's also something called topological. So there has not been a real quantum computer level implementation of that, but it is seen as a very good potential as well. And Microsoft is the main supporter of that. And Intel is trying to do both quantum dots and circuit-based ones. And in terms of the highest number of qubits, the highest number that I'm aware is a 79 qubit system. It is from IonQ, so interestingly, it is from a trapped ion system. But I think that those guys may be limited when we are trying to bump it to the hundreds. So to understand a bit more about the circuit aspects, so we need to understand this device called the Josephson junction. So this is a very, very interesting device. So if you have this device in the room temperature, it acts like a resistor, but you bring it to super cold temperatures, few millikelvins, and all of a sudden you notice that this is acting more like an inductor. And for a qubit operation, that's the regime that you are interested in. And to build a structure is also simple, in theory at least. Basically, you bring two superconductors shown as green here. Your superconductor is basically a material property, so it can be, for example, aluminum, niobium, etc. And then you introduce a non-superconducting material in between. That can be some dielectric, it can even be metal, and it can even be an air gap. But it needs to be fairly thin. So the device characteristic is also very interesting. So this is an IV plot. Let's say you try to introduce current from one direction to the other. What you are going to notice is as you introduce more current, you are not building any voltage across the two terminals between the left and right terminals. is still showing you 0 volts until you exceed a critical threshold here, and all of a sudden you jump to this point, and all of a sudden you have developed a discrete voltage. And from then on, if you try to increase your current, your voltage is also linearly going to increase. So in this scheme, actually, you are working more in the traditional regime of things, where you are actually tunneling electrons across. But until you get to there, you are actually tunneling Cooper pairs, basically 2 electrons that are always traveling together, and there's no electron tunneling in this regime. So there's a simple formula that defines this region alone. So whenever your voltage is 0, you are still developing some phase difference between those left and right terminals. And the C stands for critical current, and S stands for the superconducting current. So this was invented by Brian Josephson, got a Nobel Prize, and he's still alive as far as I know. So this device can also be represented by this symbol, which is like a rectangle with a cross in it. So now, how can I build a circuit-based qubit out of it? And there are multiple ways, but the qubit that has shown most potential so far is called the Transmon qubit, which is basically a capacitor brought in parallel to that Josephson junction. And so this shaded box is going to give you a qubit. And then you use additional capacitors to couple this qubit to the outside world. For example, it could be coupled to a resonator, which can either couple to other qubits or an I/O port. So here is an example of an earlier versions of IBM's supercomputer. In this case, 4 qubits are shown. So 1, 2, 3, 4. And what you see in between those long lines are resonators. Each of them are resonating at a specific frequency. And each qubit is also oscillating at a specific frequency, and you try to actually set the frequencies apart from each other so that they are not affected by the noise of each other. And then there are other resonators that couple it to an outside world. So these can be your I/O ports where you introduce your signals and read them out. So these are some more recent, not most recent, but some more recent architectures from IBM. And in this representation, you are seeing some I/O ports on the left and right. And again, those squiggly lines are the resonators, and then the qubits are shown as dark rectangles. And depending on the architecture, you might have a different number of connectivity between your qubits. So here your qubits are shown in these circles, so it's a 20 qubit system. But you see that some of the qubits are coupled to more qubits than others. So this may depend on the way you design your layout and how you place them. And some of the characteristic parameters we discussed are measured for these, and these are measured daily and multiple times a day to make sure that the system is operating within the specified bounds. So, for example, the frequency of this system was above 5 gigahertz, and T1 values were about 44 microseconds, T2 21 microseconds. So there are some devices where these numbers have exceeded 100 microseconds already at IBM. And then gate and readout errors, which you try to keep as low as possible. Also, the names that you see here are are not necessarily where the quantum computer is hosted, but I assume that there are some research groups, let's say, for example, in Tokyo. So those kind of other factors have come into the naming of these systems, but they're all in the cloud and accessible usually. So since there are those gate errors, etc., then we need to also start worrying about maybe error correction. And I tried to describe one way of doing this. And there's going to be an ancilla qubit which is trying to measure the qubits that are in the vicinity. Let's say this one is trying to measure these 4 green ones around it, and then it's going to take it's going to use CNOT gates and see if any one of those is giving you is going to try to invert this ancilla, and if it gets one inversion, then it's going to indicate that there was an error in that computation, and then you are going to try to maybe repeat that, or maybe some other solution to account for that. So there is really not much limit on how much error correction you can introduce. So, for example, you can use 27 qubits to describe one logical qubit, and all the rest of those 26 qubits could be helping in improving your error rates. So you decide that number by a given circuit, the error rates you have, and then you would try to introduce some error correction. So since we currently have limited number of qubits in the tens, we are not able to do a very strict error correction. But over time, we will need to introduce more and more error correction. So in terms of what we have done, as some of our original work, so that capacitor that goes in parallel to the Josephson junction, that can take a very large area. So it can be like 100 times the area of a Josephson junction. And basically, the qubit area was pretty much limited by the capacitor area. So we worked on trying to introduce some vertical capacitors to reduce the area of those capacitor that goes into the transmon. And we were able to just use standard capacitor formula for this. So assuming this niobium is our superconductor, we tried going into the silicon to form our capacitor. So it's going to couple a bit through the air, but a lot of the coupling can also be through the silicon as well. And when we went through these formulas, we noticed that we are able to reduce our area of this capacitor to 6% of the traditional flat capacitor. So we have described our structures in this patent, for example. And we also introduced another version of that. So by introducing kind of 2 trenches where we fill the inside of the trench with superconductor, but they are separated by a silicon. So it turns out that this particular structure was giving a much better reduction. So we were able to go down to 1.5% of the original capacitor area. So what's the roadmap ahead look like? And so IBM kind of want to put a stop to the fights in terms of just increasing the qubit counts, because it is possible today that we can have a quantum computer with 1,000 qubits. There's not much of a manufacturing challenge, but when you try to characterize it, you will see that there are so much errors in the system. And this new metric was introduced by IBM research colleagues, and it is taking into account not only the qubit count, but also how deep you can go with your computation without running into significant errors. And you take the square of the depth of the computation, and you take the minimum between the qubit counts. So IBM is suggesting that this is the metric that quantum computers should be compared, not just the qubit count. And they have a roadmap that looks like this. So with this metric, we are at 16 using IBM Q System 1, for example. And for those of you who are more into the software aspects of things, IBM has this great project called Qubits, which is also an open source project, and it deals with trying to convert user inputs to a given quantum circuit. So you are welcome to contribute either within IBM or through maybe the external channels. And I'd like to also thank Regine Malik as well. So that's all. Any questions?
Talk about qubit errors. Is that when the qubit is in that in-between state in the spherical model? Is that where you have to? It's either going to be a 0 or 1 in your
So even though, let's say it is pointing to some place at the current time, maybe 10 microseconds later it has shifted somewhere else, and it's even possible it started shifting to the bottom. So one error is coming from whether the qubit itself is able to maintain its state, but also when you are applying gate operations, these are usually done through introducing some microwave signals to kind of make those resonators oscillate and couple qubits. So those also can introduce errors, and I'm not too familiar with those ones, but yeah, I think those are the two sources of errors.
It sounds like errors are a problem to solve.
What is the program? Is it the microwave influence to the resonators?
So the program is basically the circuits itself. So let's say you are trying to solve a particular problem, you would come up with an algorithm, and then you would need to map that algorithm to this representation. So that would be the circuit. So there are also simulators for that. You don't need to try the actual quantum computer, but IBM has also developed some simulators where you can also use traditional computing power to simulate such a circuit as well.
And one more question. The entanglement is a mystery to me. I mean, it seems to be a key part of this. How do the particles become entangled?
Yeah, I mean, there are a lot of theoretical discussions around that. For example, some theorists believe that you can only entangle 2 qubits at a time, whereas I think with my earlier definition, which I'll just try to bring this back up. So this is how I tried defining it. It's kind of working your way back around. But if you measured one of the qubits and then you realize later on that the chances of you getting a 0 or 1 from another qubit changed as a function of what other qubit you have measured, I think you can assume those qubits at least were entangled.
Rashid, what are the pain points that you foresee in achieving greater performance in quantum computing?
So it is. So it's a rapidly expanding field, and people are trying to figure out why they are observing certain errors. For example, why we are not able to have a qubit that gives us 1,000 microseconds instead of 100 microseconds. And they discovered that the way you manufacture the qubits, if you are like very cleaner in your process, it can make a difference. But they need to discover these by running multiple manufacturing cycles and trying different ideas. And there are not very clear theories that link the errors to the manufacturing either. So all of those are still being discovered, and that's so basically, we need to bump up those T1 and T2 numbers. We need to also make sure that we are able to have circuits that have large enough depth, let's say 40, 100, whichever is sufficient for the theoreticians to solve meaningful algorithms with a quantum computer. So it's work in progress.
Is there any link between temperature variations and the error rate of the qubits?
So the temperature in the system is quite stable. Yes, but still, yes. So that you may still observe day-to-day variations, but they are not very high. Except if you bring the whole system back to the room temperature for any reason, and then cool it back, then you will see a huge difference. But yeah, if you keep it cold, it is quite stable there.
Thank you.
There are some people who are online, so I'm asking them if they have any questions. I don't see any questions online. Do you want to check them?
Is it left on?
Yeah, it's still open.
I invited one colleague, so I can follow it.
Good. Okay, so thank you very much for attending. I would like to thank Rashid for sharing his expertise.